Okay, this is the section 8.2 notes for the online trig class. Inverse trigonometric functions continued. We're now going to be looking at those reciprocal functions after we do one more thing with cosine, sine, and tan. There's one piece there left with those, and then the other piece of this is what do you do with secant, cosecant, and cotangent. So last time we learned that if you had cosine and then cosine inverse inside, because you're composing the same function with its inverse, as long as the argument was within our restricted domains, the answer was just the argument. This is a little bit different because in our first exploration here, essentially it's cosine, but inside it's tan inverse. So we have to think of this a little differently because cosine and tan inverse they're not inverses of each other. You can't just compose and say it's 3/4. So let's walk through how we could consider solving this problem. So remember that tan, you can think of this as its own little separate piece. You let tan inverse of 3/4 equal a theta, because essentially when you plug into a cosine, you should be plugging in a theta. And that means that we can then swap these and go back to being original tan. Remember, that's just like swapping your x and y. So it's changing it back to its inverse. So this would be tan theta had to be 3/4. Now let's remind ourselves what we learned about tangent last time. Tangent is in quadrants 1 and 4 when you talk about inverses. Those are our restricted domains. So negative pi over 2 to pi over 2. Then we have to also think, okay, this is 3/4. That's a horrible 3. This is 3/4, which is a positive value here. So remember, all science teachers are crazy. Tangent is positive in quadrant 3 and quadrant 1. So since this is a positive ratio, that means we have to be in quad 1. I said quad 1 and wrote 3. So quad 1. Now, what we're going to do next is put what we know about this triangle on here. So we had that tan of theta was 3/4. So this is our theta. It's our reference angle. Tangent, remember, is opposite over adjacent. So that would be 3 for y and 4 for x. And notice that this is just a right triangle, so we can find r by doing Pythagorean theorem. So 3 squared plus 4 squared equals r squared. That's 9 plus 16, and that's 25. And we know that that square root is 5. And that's essentially all you needed. You needed to locate the correct quadrant so that you would know what the signs of the numbers would be. Hypotenuse is always positive, but since this is quad 1, both x and y are both positive. Because if you have positive 3/4, you could have also had a negative over a negative depending on what quadrant you're in. So you just have to make sure you watch your signs. And then we're just going to answer this by looking at this picture. We don't even need to know what theta is. We don't care about theta. What we want to know, because remember what I said last video, is that when you're dealing with these problems, if you had tan inverse of 3/4, 3/4 maps to a theta, and then cosine of theta is going to map to a ratio. So you have a ratio on the inside function, you map it to the theta, especially since this was a inverse, which means this is the ratio, we map to the theta. The outside function was the cosine, and you now have that theta, and you want to map it back to the ratio. Never did we need to know what the theta was, because we just needed to map there, get the picture of the triangle, and then find the correct ratio. So cosine is x over r, so that's 4 over 5. And we're in our correct restricted domain, we're in our correct quadrant, so this is the answer. Okay, so that was the last piece of those. Let's do one more example just to drive it home. So I have sine inverse of negative 2/5. First of all, I didn't say this in the last one, but before you even attempt to solve this, especially if there's an inverse inside, you have to make sure this is between -1 and 1. So this is between -1 and 1. So we're good there. We need to figure out where, so that means that theta equals sine inverse of negative 2/5. So if we change that back to just being regular sine, it would be sine theta equals negative 2/5. So I need to draw my picture. That always helps me. And remember that sine is also defined from negative pi over 2 to pi over 2 when you're talking about inverse functions. Our little saying goes, all science teachers are crazy. We need our sign to be negative. So this is where everything is positive. Sine is positive over here. Tangent would be positive, so sines are negative, but that doesn't help us. Cosines are positive, so sines are negative. So that means we're down here in quad 4. So I'm going to draw me a little right triangle. So there's my theta. So remember, sine is opposite over hypotenuse. So this would be 2 and 5. Hype is always positive, so remember this is a negative y value, so that's a negative 2. So this time you have negative 2 squared plus an unknown x squared equals 5 squared. That's 4 plus x squared equals 25. Subtract over the 4 and we get 21. So x is the square root of 21. And it is positive because the x's are positive on this side. So then we're supposed to do tangent of that theta information that we have. So here's our theta. So tangent of theta is, remember, opposite over adjacent. So that's negative 2 over the square root of 21. And we have to rationalize that. So multiply top and bottom by square root of 21. So my final answer to this big thing is negative 2 square root of 21 over 21. So we mapped the negative 2/5 to the correct quadrant, got our signs correct, and then we mapped the theta part, which is the angle attached to this triangle, to the correct ratio on the outside they were looking for. Okay, so that then takes us to defining the inverse secant, cosecant, and cotangent functions. They have all these definitions in the book and in the pictures. I want to show you how I came up with this part right here for both of these. So secant and cosecant inverse, remember, they have to do with how did we find the graph of secant and cosecant? Remember, because secant is the reciprocal of cosine and cosecant is the reciprocal of sine. So I want to show you, we did this before in the previous chapter, so I've already got some graphs set up here. We're going to start off with secant. So here's what secant looked like. Remember, it was cosine kind of was a wave that ran in between here, and we found out that when you flipped the fractions of cosine, you got these like parabolas that had asymptotes that they couldn't cross. So that's kind of where we were at last time. If you take all of these ordered pairs, say this is the ordered pair negative 7 ish, so negative 6.54 and 1.034. So you can kind of move along. Find any of those ordered pairs. An inverse, so negative 2 pi comma 1. An inverse, remember, takes all of those points and flips them. So the inverse, and we didn't talk about this a lot last time, but secant to the negative 1 is one way to write the inverse. We also use this arc secant. That's another way to write an inverse instead of using the negative 1. Before I do that though, remember a secant, if you want to get the inverse, you just swap the variables. So if I do that, you can kind of see this crazy thing starts happening. So remember this was negative 2 pi and this was 1. I believe we can find out that, yeah, that's negative 1, 2 pi. So that's not the exact match I was looking for. Positive 1, negative 2 pi is what I'm looking for, which I believe is down here. Yeah. I don't know if I can show this in this screen. Hang on just a second. Back out a little bit. There we go. So see how crazy this looks. Here's negative 2 pi 1. The inverse match of that is down here, 1 comma negative 2 pi. So all of these guys, the vertical ones, have a matching one that is now horizontal. Now that gets really dizzying to look at. So if you use the arc secant graph, this has already been, they've taken into account some of that stuff. Notice that they give you just two little chunks. Now you think, well, why didn't they give me a full parabola shape? There's a reason for that. Because if you had a parabola here, you would fail the vertical line test. So what they do instead is they start at 0, because that's a nice point for this graph, 1, 0. So the height of 0, and they end it at a height of pi. So notice that's the height that they end at. So that's the y value. And the reason they do that is because you get all the values on this parabola without crossing itself vertically. And then you get the lower half of a parabola up here. So we're getting all the values of x all the way across except for a few pieces in here. And we're getting a height of 0 to pi. So that's the highest that this reaches. Now, notice that there's a whole missing chunk here in the middle. This is -1 to 1. See that? That's missing right there. So what's going on here, and this is kind of where my domain and range came from. So this is the arc secant is going to be our inverse. And remember, it's a restricted domain. So notice this is where I got this. The x values that show up on the graph are either bigger than 1 or less than -1. That's what this absolute value actually means. This piece of information right here says that x is farther away. Excuse me. I need to write it differently. Talking and writing doesn't always work. Why is my eraser not working? There we go. X is either going to be less than or equal to -1, or X is going to be greater than or equal to +1. We are saying my distance from 1, I need to be bigger than that. So to go away from 0, to go farther away, you have to go to -1 and keep going to the left, or +1 and keep going to the right. So that's where that came from. That's what that actually stands for. And we noticed that the y values used here went from 0 to pi, but there was a problem. You had these asymptotes here, we have an asymptote there. There's a line here that this never crosses. It gets high close, but it doesn't ever cross it. That is pi over 2, because that's the same issue you have vertically. So it's everything from 0 to pi except for pi over 2. Right, so let me go back to my graph. We can talk about the cosecant. So here's the cosecant graph. Very similar, just off-centered a little differently. And if I just switch the, I don't know why that says 7 down there. If I just switch the x's and y's, again, I get this crazy, all of my vertical ones are now horizontal, and you have that rule still that if this is -3 pi over 2, 1, then down here there should be a match that has swapped those two x's and y's. So that means this is truly its inverse. Well, we don't want to look at the whole thing. We want to look at just a small piece. Notice that you could say, well, let's just deal with maybe the bottom half of this one, because so they try to stay pretty close to 0. So notice this has the height of pi over 2, and that would give us the bottom region of this parabola. And then if we go down to -pi over 2, we could do the top half of this parabola. So that's exactly what they came up with. So notice you go from a height of, if it'll let me touch the right point. I don't want the intersection point. All right, anyways, this is -pi over 2. This is +pi over 2 at the height. And notice that we still don't cross a certain point. There's this boundary where they don't cross. This time it's 0. So, and you still have that gap where nothing between -1 and 1 is being used, because this is the reciprocal of the sines and cosines. So we go from -pi over 2 to pi over 2 for our height in our restriction, except we make sure that we don't use 0. And if you look back at the original, that's because we had a vertical asymptote at 0. Okay. Let's go back to our video and our notes. So on similar lines, we could do these things for cosine, right? Or for cotangent. So let's get rid of some of these. So to talk about cotangent, we need to remember what tangent looked like, which remember looks like this. cotangent, which was its reciprocal. Remember, they just flipped the other way, so this is cotangent. If you swap your x and y, you notice that you get these. They're really fun to look at. So it's all of those same little slanted lines now, but they're now horizontal. So we don't want to look at all of that at the same time. We want to look at what would they say is the restriction. So arc cotangent of x, and we need a y out front. So notice here, because the graph has this nice continuation, I'm going to take away this one for just a second. Notice that this passes the vertical line test, so we don't have to do any chopping there. So our x's are actually negative infinity to infinity. We can use any x on the number line. But we do have a restricted range. We never touch the 0, and we get really close to, but we don't actually cross. Notice we're at 3.011, 3.067. This is hovering at pi. So from 0 to pi. So let's fill that in on our little chart over here. So our cotangent, you can go from negative infinity to infinity for your x's, but you have to restrict your range. And notice it does not have equal to. Those are asymptotes. Okay, so this is just our domains and ranges, or our restrictions. These are our restricted values for these three inverses. So let's look at an example. So we want to do inverse of cotangent of square root of 3 over 3. That means that our theta, the interior part, would be cotangent of inverse of square root of 3 over 3 means that we can rewrite that or swap it. If we swap, you have to change back to the original cotangent. So cotangent theta is square root of 3 over 3. Now, cotangent's not one of our main three functions that we deal with the most, but remember, all science teachers are crazy. That's the most helpful saying in trig. Helps you figure out your quadrants. So remember, go up here and look at cotangent. You can use any x that you want, but our range has to be restricted, which means we're from 0 to pi. So we are in this 0 to pi quadrant restriction. Okay. So look at this. Over here, everything is positive. So all the different signs. Over here, sine is positive. Sine and cosecant would be positive over here. All trig functions are positive over here. So we're going to have to be in quadrant 1. Okay. Now, some people don't like dealing with cotangent, but remember, cotangent and tangent are reciprocals, so that means that's 3 over square root of 3. So if you think about that, that means this is y over x, so 3 square root of 3. And this is positive and this is positive because we're in quadrant 1. So we need to do Pythagorean theorem to find the other piece. And then we need to figure out what this ratio is. So this would be square root of 3 squared plus 3 squared equals r squared. So that's 3 plus 9 equals r squared. And that would be 12 equals r squared, which means r is the square root of 12. Or you could think of that, remember, as 4 times 3, which would be 2 on the square root of 3. So we didn't even actually have to go through labeling this triangle because this right here is a special ratio from the unit circle if you know all of your tangent combinations. Most people don't memorize tangent from the unit circle because they know the sine and the cosine parts because that's the x and the y ordered pairs. Remember, it's cosine for x and sine for y. The reason I did this was because if you can get it into this format, you can see which special triangle it is. It doesn't look quite right yet, but if you divide, in fact, I could have left that as 3 over the square root of 3, but if you divide everything by a square root of 3, and that's okay if you do it to all sides of the triangle because it's proportionate, then you would see that this triangle comes out as a 2 on the top, a 1 on the bottom, and 3 squared root of 3 gets rationalized, which means you 3 over the square root of 3, you multiply top and bottom by a square root of 3, and then the 3's cancel, so it's just square root of 3. This is the 30, 60, 90 triangle. So remember, in our triangle, the 1 is always across from the 30, the 2 is across from the 90 degrees, and the square root of 3 is across from the 60 degrees. So this is a 60-degree angle. Usually when we do inverse angles, though, we want it in radians. So remember, 60 degrees times pi over 180, it ends up being pi over 3. So you didn't have to go through the whole picture and draw the triangle out, but if you're going on to calculus, if that's your goal, you really need to be able to draw any right triangle in any quadrant, label it, and find pieces of information, because if you can't memorize everything that's out there, and honestly you just can't, you can't memorize everything that's out there in trig, there's too much, being able to resort to the triangles is always the best case and backup if you forget something on an exam. So that is the first example of that. Okay, so let's talk through what we've learned about secant inverse, cosecant inverse, and cotangent inverse, or if you want to call them, arcsecant, arccosecant, arccotangent. So look back up at our list. So the range of secant was 0 to pi, with pi not equal to, or with y not equal to pi over 2. And those are not equal to, are they? Yes, they are. Okay. So 0 to pi with y not equal to pi over 2, which is the same as the cosine function. Remember, except for the pi over 2 part, because cosine could equal pi over 2. But the 0 to pi part matches up with that. So to find the inverse of the secant function, if you don't have a nice value, if this had not been square root of 3 over 3, if it had not been a 30, 60, 90, or if it had not been, a 45, 45, 90 triangle, you can still find the inverse if you realize that it's similar to cosine's quadrant behavior. So to find the inverse secant function, you'd first convert this to cosine, which means, remember, it's reciprocal. The range of cosecant, go back up here, is negative pi over 2 to pi over 2. So negative pi over 2 to pi over 2. And this would be inverse function, by the way. So negative pi over 2 to pi over 2. And we knew that pi could not equal, or y could not equal 0. That's similar to, remember, the sine inverse function. So to find the inverse cosecant function, you'd need to convert to sine inverse first by making it its reciprocal, and then you could use your calculator, because your calculator does not have these buttons. The range of cotangent inverse is, if you go back up to our list, is 0 to pi. Except this time it is not equal to, yeah. So we need to throw that out because our asymptotes are 0 and pi instead of being stuck in the middle. So this means that we would also use the cosine inverse function to help us approximate. Write that out there. So two of these, actually, if you don't have a nice value, in other words, it's not something on the unit circle, two of them would be used cosine inverse as kind of a guide, find that approximation, and that will help us find the cotangent inverse of that piece. And then one of them uses the inverse of sine. So our last page is focused on two things. We're going to use the rules that we just came up with of how do I evaluate these to use our calculator for things that are not nice ratios of our unit circle values. Then we're going to come up with some properties for substitution at the very end. That's the last exploration. That's going to help you guys going forward into some of the new stuff coming up down the road. So let's look at these. So it says use a calculator to approximate each expression in radians rounded to 2 decimal places. Okay, so let's look at this secant inverse of 5. So theta equals secant inverse of 5. Let's look back up at our rules, remember, because that's always where you want to reference. Secant inverse, remember, was the same as cosine inverse in terms of our domain. So we can think of, first of all, if this is our inverse, then secant theta equals 5 when theta is between 0 and pi, but not pi over 2. Okay? The reason that's good is because 1 over secant theta is cosine theta. So that means we would just need to flip this. So that would be 1/5. So then we can say, okay, cosine theta is 1/5. So theta is cosine inverse of 1/5. And then we can use our calculator to help us find the ratio from there because, or the angle for us, I should say. We need to be in radians, but because this now is something that we have on our calculator. So 1 divided by 5, and then we want to take the cosine inverse. So that's 1.37. And that's it.